All right, so let's talk about spectral clustering, which is a more advanced clustering techniques in comparison to very simple k-means clustering, for example. And the idea is that you want to minimize the ratio cut of A and A bar. Before that, I think I need to talk about these points. We have n points, and we want to have a notion of similarity. So, the clustering is an ill-defined problem. No one can say which one is wrong, which one is right. It depends on which perspective and which one is more important. For example, it's like multi-objective optimization. You have a set of solutions and your Pareto optimal set, and any of them are the solution. So you cannot say which one is better than the other. So it's an ill-defined problem. So you need to make sure which one is more interesting for you. So we construct a weighted undirected graph. Let's say this is your graph. We have vertices, let's say these are nodes, and some edges. And we cut the graph G into two parts. So you have a graph, something like this, and you want to cut this graph into two pieces, A and A bar. So the idea is that nodes on one subgraph, for example this one, is nodes on one subgraph are similar. Of course, nodes on this subgraph is also similar. For example, these are those faces who have glasses, and these are faces are happy, wink, anything. So we have two different classes. But the goal is not classification. It's about clustering. You just make clusters. So we need the notion of cut of A and A bar, which is the sum of all weights between them. And I is in A and J is in A bar. So A bar is the set of nodes minus A. Let's say mathematically we write it like this. And you know that the set of nodes is the union of A and A bar. Okay, so these are preliminary things that you need to know in order to understand. So welcome to ratio cut of A and A bar. We are trying to make it more symmetric, and also there is another reason behind the definition of ratio cut, because if we just simply use a simple cut, if we have an outlier here and we have a set of points here, and then a small outlier like this, maybe you could argue that this is a good cluster. So it's very unbalanced. So this has the problem. It is unbalanced clustering. So one point, just because of one point, you are just doing. Of course, it is a cluster. You have two clusters, but it is not realistic and it is unbalanced. That's why we defined the concept of ratio cut of A and A bar, which is cut of A and A bar over cardinality of A plus cut of A bar and A over cardinality of A bar. And the claim is that minimization of Wij Fi minus Fj squared is equivalent to minimizing the ratio cuts. And of course, we define F, the coordinates of F, as cardinality of A bar over A if xi is in A, and if xi is not in A, then it is negative cardinality of A bar. And so let's just write it and you will see why they are equivalent. So I want to prove that this problem is equivalent to minimizing ratio cut, which I have defined here. So let's carry on. Ij, you can write this as just I in A, J in A bar, Wij cardinality of A plus cardinality of A bar plus, or I over I inside A bar, and this time J is inside A. So any of them could happen, and so this is minus cardinality of A over A bar minus cardinality of A bar over A squared. And this is equivalent to writing Wij plus cardinality of A over cardinality of A bar plus omega Ij cardinality of A bar plus A bar A plus 2. And you can work on that. You will realize that okay, let's do it step by step. And this is A bar A plus A bar plus 2. Instead of 2, you can write A plus A bar plus 2 Wij plus Wij I inside A bar, and this time is opposite. And so this is equivalent to 2 A bar plus A plus A plus A bar plus A bar cut of A and A bar. You clearly see that this is N. The sum of cardinalities is the total cardinality is this. This one is N again. And you clearly see that this is equivalent to cut of A and A bar. So this is just 2n ratio cuts. And we have proved the have proved our claim. And now you will see that so Fi is, just to remind you, that it is A bar A if Xi is in A and Xi is in A bar is negative. And we want to minimize Wij Fi minus Fj, and if positive in A, Fi is positive. And so our claim is that I want to prove that this is Fi minus Fj squared is equivalent to F transpose LF. And L is the Laplacian. You see, Laplacian shows up in many different methods in machine learning, and that's why it is interesting. Also, I will talk about Laplace in several videos because it's very important, from regularity conditions, from different aspects. So that's Laplacian is very important. Laplacian of graph of G, and by definition, Laplace is the difference of a diagonal and your weight. So your weight is a m by n matrix, Wi1, Wyn, Wn1, Wnn, n by n, and diagonal, this is like this, d1, d2, dn, and the rest is 0. And you know, di by definition is the sum of di is sum over j. And so let's carry on for this claim. We can write F transpose LF equal to F transpose D minus WF is equal to F transpose DF minus F transpose WF. This is a scalar, and you can write it as 1 over 2 DI squared minus 2 ij Wij Fj. This is equivalent to Di squared dj Fj squared minus 2 Wij Fj. And this is equivalent to Fi squared Fi squared Wij plus sum over j Fj squared over Wij minus 2 Wij Fj. And this is equivalent to Wij Fi squared plus Wij Fj squared minus 2 Wij Fj. And that's it. Our claim is now complete because This is equivalent to fi minus fj squared. So the proof is now complete. So minimizing F transpose LF subject to F transpose F is equal to 1. This is the solution is that it's the second smallest eigenvector of L, as I've told you before, because the first one has eigenvalue 0. Note that the first one has eigenvalue equal to 0. So if fi is greater than 0, xi is in A. If fi less than 0, xi is in A bar. And this is just the spectral clustering. But the reason that I talked about spectral clustering is to show you how Laplace play an important role, how it plays an important role, and that's why now I start by Laplacian Eigenmap, which is personally I like it more than locally linear embedding for many reasons, and it captures a nonlinearity better than any other method. I mean the methods that I've talked so far, and the idea is that it's similar to what we have done for the definition of graph. We have graph V and E, vertices and edge. So we create this graph again by saying that the weights of this graph, if I and j are connected, it is 0. It is 1. And otherwise, if they are not connected, it is 0. You can define this weight. You can define any kind of weights as long as it is a good measure of similarity between points. But the alternative is that Wij is xi minus xj. You know, many people talk about these distances, but you know, you should find the intrinsic geometry of that, and for defining the intrinsic geometry, you need to understand your metric, and so the inner product in the tangent space. So that's why all of these distances are just not complete, and because you don't know the intrinsic geometry. So the only thing that you can do is to approximate it by some distance functions like this. So we want to minimize, first of all, your x is d-dimensional, is too big. It's high dimensional. You want to reduce it. You want to reduce it to a lower dimensional space, Rp, where P is very, very less than D. So you want to minimize Wij, y, so we're penalizing yi minus yj by Wij. You're penalizing this. So if xi and xj are far apart, if xi, xj are far apart, Wij is equal to 0. We don't care about values of y. But if xi and xj are very close to each other, then